Hi, this is Girona from Elektrobit Automotive GmbH, and I'm going to do a screencast of my Eurographics 2013 presentation on data parallel decompression of triangle mesh topology. This is joint work with Benjamin Keinert and Marc Stamminger from the University of Erlangen-Nuremberg and Gerd Sussner from RTT AG. Triangle meshes are one of the most important data structures in computer graphics to represent geometry. And in this talk, I'm going to focus on the topology of triangle meshes. Topology, that is the way vertices are connected to form triangles. So for example, the red triangle here consists of the vertices 7, 6, and 4. The gray triangle consists of the vertices 1, 8, and 7. And by taking down the triples for each and every triangle, we get a representation for the topology. And it's particularly interesting to compress triangle mesh topology because in a typical mesh with positions and normals, topology amounts for about 50% of the data. More precisely, a triangle stored on a GPU consumes 96 bits, and we can take these 96 bits down to 1 or 2 bits per triangle using existing triangle mesh compression techniques. You can look up the most important ones in these overview reports shown on the right. The way these methods perform decompression is as follows. They start with decompressing the first triangle, and then they decompress the second triangle using information from the first triangle. And likewise, when decompressing the third triangle, they use information from both first and second triangle. And this makes triangle mesh decompression with existing methods a truly sequential process. One way of accelerating this process is to increase the clock rate of the processors. However, that is not the way computers get faster today. They get faster because chip manufacturers are putting more and more cores onto their processors. And clearly, on such a system, a sequential decompression technique has disadvantages because it can use only one core and therefore it uses just a fraction of the total computational power available. And the situation is even more severe on a GPU or graphics hardware where we have hundreds and thousands of cores. On GPUs, we do not want to run sequential algorithms, we want to run data parallel algorithms. Data parallel algorithms are algorithms that use all computational cores to simultaneously solve a common task. We were looking for such an algorithm. However, we were not able to find an algorithm that carries out data parallel triangle mesh decompression on a GPU, and therefore we had to come up with our own algorithm. We picked the following two requirements for our new algorithm. First, we wanted real-time decompression on a GPU, and second, we wanted high compression rates. A naive approach for decompressing triangle meshes in a data parallel fashion on a GPU would be as follows. We take an existing mesh and create multiple submeshes out of it, and then compress each submesh using an existing triangle mesh compression technique. Then, each compressed submesh is assigned to one thread, and each thread carries out a sequential triangle mesh decompression algorithm. The problem is, however, that multiple threads share common resources. For example, the threads marked gray here share a common program counter. That means that they have to be at the very same line of code at a given point in time. This can become a problem, however, once they run across the switch statement here. It might happen that each thread wants to go into a different branch. And this cannot be achieved with just a single program counter. What the GPU does is, it serializes these four threads. So with the approach of decomposing a mesh into multiple submeshes, we get no parallelization at all. Instead of having these complex computational kernels, we wanted to have simple computational kernels. Ideally, each thread only outputs one triangle, and this is the design guideline of our algorithm. In order to achieve good compression rates, we order the triangles. We start by picking a seed vertex, and from that seed vertex, we take the triangles in its neighborhood, and add those triangles to the first belt shown in blue here. Then, we take the boundary vertices of the first belt, and add triangles in their vicinity, which are not yet part of the first belt, to the second belt shown in green here. And we continue by taking the boundary vertices of the second belt, and look which triangles are in their vicinity and not yet part of any other belt and add those to the third belt. We continue this process and thereby we create new belts. These belts order the triangles in a breadth-first fashion. We use this breadth-first order to create generalized triangle strips as follows. We start by taking triangles from the first belt to create generalized triangle strips. And once all triangles from the first belt are part of a generalized triangle strip, we continue creating generalized triangle strips by picking triangles from the second belt up until all those triangles are part of a generalized triangle strip. And then we continue adding triangles from successive belts up until all triangles of the mesh are part of a generalized triangle strip. We store generalized triangle strips on the GPU using two arrays. In one array, called C, we store a 1-bit code for each triangle, and in the second array, V, we store one vertex for each triangle, except for the first one, where we store all three vertices of that triangle explicitly. The triangle neighboring the gray triangle can either be across the clockwise edge, which we call the N edge, or it can be across the anti-clockwise edge, which we call the P edge. In this case, the blue triangle is across the P edge, and therefore we take down P as the code for that triangle, plus we have to take down the new vertex that comes with the blue triangle, which is a 2 in that case. The triangle next to the blue triangle is the green triangle, and it is across the N edge. Therefore, we take down N as its code. Furthermore, it has a vertex, which is a 6 in this case, so we take that down too. And we continue adding codes and vertices for each triangle up until we have created a code-vertex pair for each triangle in the mesh. Unfortunately, the GPU cannot use this representation for rendering directly. It can, however, use this representation shown at the bottom of the slide, which uses 3 vertices for each triangle. And therefore, we need a way of converting the compact representation showing at the top of the slide into the representation shown at the bottom of the slide. And we do this using CUDA. So at first sight, it might almost seem impossible to do this conversion in parallel on the GPU using CUDA, because every triangle directly depends on its predecessor, and that would suggest using a serial algorithm. But I will show you now how we can reduce the sequential dependencies to a very low level. So the first triangle is a special case, for which we have to copy the vertices shown in black from the top down to the bottom. Further, we see that the remaining vertices in V correspond to the third vertex of each triangle. Therefore, we can simply copy those down too. Further, whenever there is a p-code, we see that the triangle's first vertex is right before the p-code within the V array. And here's another example. And likewise, whenever there is an encode, we find the triangle's second vertex right before where that encode is within the V array. One more example. And here's another example. And we have another rule whenever the code changes from N to P. In that case, the triangle's second vertex is right before where that code change occurs within the array of vertices. And here's another place where this rule applies. There's also another rule whenever the code changes from P to N. In this case, it's the triangle's first vertex, which can be found right before that code change within the array of vertices V. And here's a second example. What's left in this example here is the double encode, but that could theoretically be an entire series of encodes. And we would find the first vertex of the corresponding triangle right before that P which precedes the series of encodes. The question is, how do we find out that particular location to which the orange arrow points to? The answer is, we introduce another level of indirection. In our case, this indirection comes in the form of the array Q bar. This array Q bar has one entry for each triangle. The entry's purpose is to guide us to the appropriate index location within the array of vertices whenever we have a double encode. In that case, we can read the triangle's first vertex from the array of vertices. We compute the array Q bar using the helper array Q. Whenever there is a code change, we store the corresponding index location into the respective element of the array Q. We do this every time the code changes from N to P, but we do this as well if the code changes from P to N. In case there is no code change, such as with these two N's here, we take down a 0, and you will see in a couple of seconds why this makes sense. For the remaining elements, we only have code changes, so we proceed as we've done before. Now, we transform the array Q into an array Q bar using a maxscan. A maxscan operation is an operation that runs extremely fast on a GPU because graphics hardware manufacturers are providing well-optimized libraries for this task. So a maxscan works as follows. We initialize the first element of Q bar with a 1, and then take its maximum with the second element of Q, and write the result into the second element of Q bar. And we do the same thing for the next element and all other elements of the array Q bar. Now with the array Q bar, we finally have the desired level of indirection. So every time we see a double encode, we perform a simple lookup into the array Q bar, and that will lead us to the correct location in the array of vertices V. And in the case of a double encode, that will give us the first vertex of the respective triangle. Note that we can use the very same array Q bar to handle double P codes as well. In that case, this will concern the second vertex of every triangle. So after having computed the array Q bar, we use one thread for every triangle and apply the set of rules that I've just shown you to decompress generalized triangle strips into the representation the GPU can use for rendering. This gives us an extremely high level of parallelism, as each triangle can be decompressed independently from all other triangles using one thread for each single triangle. We have tested our algorithm for compressing and decompressing generalized triangle strips on the model of the Welsh Dragon. The color coding shows you the way we generated the belts that we used to generate generalized triangle strips. The model has about 2.2 million triangles. When rendering the model without any compression, we use 96 bits for each triangle on the GPU, and rendering takes about 6.5 milliseconds. When using generalized triangle strips, we can take these 96 bits down to 34 bits per triangle. And we have to use CUDA to do the decompression, and that takes about 0.69 milliseconds that add on top to the rendering time. Analyzing these 34 bits per triangle, we see that 1 bit goes into the code for each triangle, and the remaining 33 go into the vertex for each triangle. So it's only just natural that we continue compressing that. Next, we do something which is very common with triangle mesh compression techniques, and that is, we re-index the vertices incrementally. So we start with the first vertex, which happens to be a 1 in this case, and replace it by a 0. Then we proceed to the next vertex, which happens to be an 8, and replace it by a 1. We have to make sure that we get all occurrences of the 8 in the array of vertices V right. And then we proceed. We simply increment and counter in case we see a new vertex and assign the counter's value to that vertex. We use the fact that many vertices are now a simple increment of a counter to do further compression of the vertices. We do this using the array inc, which holds 1 bit for each vertex. Whenever the respective vertex is an increment of that counter, we take down a 1, and whenever that's not the case and we reference a vertex that has already been there, we take down a 0. We can reconstruct those vertices which are increments into the incbar array using an add scan. The add scan works in a similar way as the max scan does that we have used to decompress generalized triangle strips. Most importantly, it runs extremely fast on a GPU. And the add scan works as follows. We initialize the first element of the incbar array with a 0, and then add this to the first element of the inc array, and write the result to the second element of inc bar. And then we do a similar thing with the next element, and so forth up until all elements are add scanned. And note that this add scan runs extremely fast on a GPU, and there are well-optimized libraries that help us performing this task. So after having performed the add scan, we see that those elements in the V array and the inc bar array, which are highlighted black, are the same. So essentially what we have done is we have decompressed the elements from the inc array to the inc bar array, which are highlighted black. However, those elements are not decompressed properly, so we have to treat them specially. Therefore, we store them explicitly in the array U. Then, we assign one thread for each element of the inc array to perform the following procedure. Whenever a thread sees a 0 in the inc array, it takes the corresponding index location and subtracts it from the corresponding scanned result, and that gives an index into the U array from which we can read the appropriate vertex. And here's another example. And here's the final one. So after that procedure, we see that the elements of the inc bar array correspond to the elements of the V array, which is the array that we wanted to decompress in the first place. So on our example mesh, this incremental vertices technique reduces the number of bits per triangle from 34 down to 20, and we have to run that add scan and that kernel for decompression, and those take about 0.46 milliseconds in CUDA. So if we look at these 20 bits now, we see that 1 bit goes into storing the code for each triangle, 1 bit goes into storing whether the vertex is incremental or not, so the remaining 18 bits must therefore go into the non-incremental vertices U. So let's continue with compressing this array. For demonstration purposes, I give you a little more complex example of how the array U could look like. And there, we're making two observations. The first one is that the values increase the more we go to the right, and that is not very good for compression, because the larger the values become, the more bits they require. The second observation is that neighboring elements do not differ much in value. So instead of storing the actual values, we store the difference between neighboring elements, and they are very small, and therefore they require only few bits. And we can undo that with a simple add scan on the GPU, which runs very fast. The question now is, how do we compress the array D? And there, we're using a technique which is called Simple 9. And for this technique, we were able to come up with a data parallel algorithm that runs on the GPU. So Simple 9 works as follows. We're taking a 32-bit word, and from these 32 bits, we're using 4 bits to encode a selector and 28 bits to encode the codes. Whenever we write a special bit combination into the selector, to which we refer to as an A, it tells us that we're having 28 codes with 1 bit for each code. Whenever there's a B in the selector, it tells us that we have 14 codes with 2 bits each. And whenever there's a C in the selector, it tells us that we have 9 codes with 3 bits for each code. And this game continues up until we have a single code word with 28 bits. So we're using Simple 9 to compress the array of differences D. And for explanation purposes, I believe it makes more sense to write the number of bits each value consumes rather than the absolute values. So here we go. Next, we're using a simple algorithm that compresses the array D to the array S. Our algorithm realizes that these two blue guys go together with 14 bits each into 2 codes. Therefore, we are taking down H as a selector and write the result into the array S. Next, the algorithm sees that these 4 red guys go together in 4 codes with 7 bits each, and therefore we're taking down F as a selector and write the result to the array S. And this goes on up until all elements of the array D are compressed into the array S. For decompression, we suggest to assign 1 thread for each compressed code word. Then, each thread decompresses its codes and scatters them out to the appropriate location within the array D. And all of this can happen independently for each compressed code word and therefore in parallel. However, every thread somehow needs to know where it is supposed to start scattering. We will provide this information in a helper array, but how do we compute this helper array efficiently on the GPU? We do this by assigning 1 thread for each compressed code word and have each thread write out the number of codes it holds. After applying an add scan on this array, we get the final result as shown here. When applying Simple 9 to the model shown here, we reduce the number of bits per triangle from 20 down to 3.7, and decompressing Simple 9 on the GPU using CUDA takes 0.45 milliseconds. This concludes the explanation of our compression and decompression technique. So let's evaluate our algorithm on various models of different mesh complexity ranging from thousands of triangles to millions of triangles. And there we see that our algorithm is able to compress triangle meshes down to just a few bits for every triangle. More precisely, our best model compresses with 3.72 bits per triangle, our medium model with 4.61 bits per triangle, and our worst model with 7.61 bits per triangle. This is not as good as sequential triangle mesh compression techniques, which can compress triangles down to 1 or 2 bits. However, our algorithm is very fast. We can decompress triangle meshes in the order of milliseconds. To put this into perspective, we can decompress a triangle mesh up to 15 times faster on the GPU than we can render the very same mesh on the very same GPU, even when using a simple shader. In other words, we were able to decompress up to 1.72 billion triangles per second. To conclude, We were using a breadth-first layout across the triangle mesh to create generalized triangle strips. Then, we suggested a data parallel algorithm for decompressing generalized triangle strips on the GPU using one thread for each triangle. We further stored vertices incrementally to improve compression and suggested a data parallel algorithm for decompression. And finally, we were using Simple 9 for even more compression and proposed a data parallel algorithm for decompression. And all of this allowed us to perform data parallel decompression of triangle mesh topology.